Hey there! In this lecture, we're going to study the algorithm called linear regression, which is a supervised machine learning algorithm, and we're going to study where and when should we use it, in which problem is it applicable. We're going to see the different types of components a machine learning algorithm has and how we can study them and how are they important. So let's just get back to the basics. We understood that in order to identify which type of machine learning problem we have, we need to study the target variable. When we look at this target variable, we have to classify it whether it's a numerical type or is it a categorical type. So if it is a numerical data type, then it has to be continuous in order to apply linear regression. So if you want to use linear regression, the first condition is that the target value should be numerical and continuous, and it should not be categorical or numerical or discrete. So if it is a continuous value, that means it can be predicted, it can be learned through the linear regression algorithm. So we have about features, the rest of the features, which we're going to represent with the x1, x2, x3, and which is a convention, and we're going to follow this convention throughout the study of machine learning algorithms, and the label will be used to represent it by y. So this is a housing price prediction dataset. We have about x n features, and we have the target value to be price, which is represented by y. So before we move on to the linear regression, every machine learning algorithm has three components. The first component is that it will have a prediction model. The prediction model will take the X set of features and it's going to predict the outcome. After it predicts the outcome, we will compare it with the actual value and on which the machine learning algorithm will train. The second component is the cost function. The cost function is used when we compare the predicted value with the actual value, and it gives us the information about how far is the actual value from the predicted value, and that difference between them is our error. So the difference between the actual value and the predicted value will be represented as our error, and the cost of the function of the machine learning algorithm should reduce as the training proceeds. So we have to minimize the cost, which means that we have to predict such values that become closer and closer to the actual values. So the cost function gives us a metric and a measure to see what is the current status and how close we are actually to the actual value. The third component is called the optimizer. The optimizer over here does this. It is the core crux of the learning step. This is where the learning takes place, because this optimizes the weights of a function. This optimizes the weights, which we will see what we are calling weights, or you can say that it tweaks the machine learning algorithm in such a way that the actual value or the predicted value becomes closer to the actual value. So the optimizer uses the iterations to optimize the weights to get a better cost value, to reduce the cost and ultimately improve the predictions of the model. So let's look at the prediction model of linear regression. So this is how we represent the linear regression model in a mathematical notation. Over here you can look at these theta 0, theta 1 and up to theta n. So there, the first theta 0 will be our bias term, and the second and the rest of the theta starting from theta 1 will be associated with every feature which is represented by x. So if you have, let's say, 3 features, then we have 4 theta starting from 0 extending to 3. So we have theta 0, theta 1, theta 2 and theta 3. So in this way these are the theta. So when I was talking about the optimizer, these theta will have random values assigned to them initially, and as the machine learning algorithm learns, the optimizer will optimize these values in such a way that when they get multiplied with the value of x, the actual value will become closer to the predicted value. So in this equation, the notation can be represented as the y hat, the upper arrow on the y, we call it y hat, is the predicted value, n is the number of features, xi is the ith feature value, and 0j is the jth model parameter. So another name for these thetas is, you can call them as model parameters or also as weights. So these feature weights or model parameters need to be optimized. So that's why their multiplication with the x features is necessary. So another way to simplify the above equation and write it in the form of vectors, we can say that we can write as theta x. So what's happening is that the theta is the model's parameter vector. So now we are going to represent this information in vector form. So this is neat, and this also increases the computational efficiency, since we have seen before that vectors are better than loops, and we have seen when we were studying in NumPy why vectorization of these model parameters and weights are important. So X is the instance feature vector. Now what we've done is we've taken the feature space and the parameter space. We've taken all the values in the parameters and the features, and we've represented them in the form of vectors. So the important thing over here is to mention over here is that the theta 0 will be the bias term, and to make sure when we performing the multiplication that it gets multiplied with one value. That's why the x0 or x0 will be always equal to 1. So the dot product of the vectors of theta and x, which is of course will be equal to theta 0, x0, and each of the theta will be multiplied with their corresponding x. Obviously x theta will be 1, so the theta 0 will retain its previous form. So h0 or h theta is the hypothesis function which is parameterized by the theta values. So this is another, say, the hypothesis function which is equal to the predicted value. These are all mathematical notations. You will see them whenever you read these equations, whenever you study them, they will always pop up. So it's better to get used to them now so that we don't have any problems later on. So the cost function, let's talk about that. So you need to remember what is the essence of a cost function. The cost function is used to measure the error, and the error is measured based on the difference between the actual value and the predicted value. So for the linear regression, we have a cost function called as the mean squared error. I hope you have studied this function in statistics before. Even if you have not, it's okay, because it's quite simple. What it does is it simply subtracts the actual value against its predicted value and squares it, and just sums all those differences together and divides it by m. So it's averaging all the errors. So if you look at it like this way, that against every predicted value there will be an actual value. So you take the difference and then you continue the process with every other actual value and predicted value, and you take the square and you sum them together and then divide it by the total number of features there were. So that what I mean by the total number of features is that the total number of values we're going to divide. So we're averaging the values. The m over here represents the total number of rows or total number of instances there are in the data set. So the basic purpose of cost function is that we need to minimize this. In order to minimize this, we will use an optimizer to optimize the weights. So our goal over here, the final goal, is to make sure that the predicted value is as close to the actual value. In this way, when we reduce the cost function, we can get a higher accuracy. So another concept of doing this is the normal equation. We have seen the parameterization and vectorization of theta t, theta x. So the thing over here is you can do it rather than going through the iteration steps.